let's kick off. I'm Julian Wood. I'm a senior developer advocate for the serverless team here at AWS. And yeah, really thanks for joining me. I'm basically going to be talking about observability for your serverless applications. And let me just share my screen so I can get my presentation up, because that's going to be far more simpler for you to follow than listening to me rabbit on. All good? I think so. So today, as I said, I'm going to be talking about observability for your serverless applications. You can contact me or find me on Twitter at @Julian_Wood. And I'm happy to answer any questions you may have about this talk or serverless in general. So what are we going to talk about today? Well, we're going to look at what observability is, why it's important, and how it has evolved from monitoring. Then we're going to go through how to actually create, view, and query logs, metrics, alerts, and also traces in your serverless applications. I'll cover what metrics are available as standard, and these are things you don't really have to do anything, and you don't have to configure anything yourself. And then I'm going to go through looking at structured logging, and then how to create some custom metrics from those structured logs. And then I'll set up an email alert and then set up a trace to see a request flow through the multiple components of an application. I'll then show how you can combine and correlate everything that has been set up with all the logs, metrics, and traces. And yeah, don't think it's all going to be slides. I'll be showing you some actual application code and also heading deep into the AWS management console. So we don't do death by PowerPoint at Amazon, as I'm sure you know. So first of all, we need to recognize that there's no such thing as an application that never fails, one that always keeps on running, whatever happens. As our CTO, Werner Vogels, often loves to say, everything fails all the time. We must assume we will need to deal with failures, and often exactly when you don't want them to happen. With traditional monitoring, there were a whole number of layers in the stack you had to monitor yourself, from the network, storage, physical server hardware, all the way up through many abstraction layers of virtualization and operating systems, eventually up to your application itself, and also your business outcomes. I've spent 25 years as an infrastructure engineer and a lot of time setting up monitoring and alerting for many of these components across the many layers. But luckily, you and us all are building serverless applications. And so now AWS takes much of the burden off your shoulders. And so you don't have to monitor many of the layers yourself. This becomes our responsibility, one of the powers of serverless. We look after the physical infrastructure, virtualization, operating system layers, and the platform runtime. You can now focus more time on your business logic as part of your application code and data, and also having a better experience. As applications have evolved and customer needs have expanded, monitoring needs to do a lot more than watch the layers of a stack. Customer experience is ever more important. Resources are often short times and ephemeral, and there are many, many more connected parts of an application which are connected to ever more devices spread probably all over the globe. And the whole application is probably evolving at a faster rate. More deployments, often smaller in size, often to more locations. Knowing your application is performing correctly is also monitoring more than just failures. Is your application actually performing as expected, even if your monitoring dashboard is all super green? Are your customers getting the user experience you want to give them and what they expect? What's the usage of your application? You likely want to know things such as how many people are signing up, or how many page views you are getting, or what parts of your application are hitting limits or congestion. What about business relevant information? What about revenue being generated? From what geographic region are you seeing the biggest growth? How could an outage of a particular application component affect your business? What trends are you able to visualize and plan for? And so we come on to the concept of observability. And this is actually a term which is derived from control theory. While monitoring may be seen as probing, querying, and reporting on the different parts of your application, observability can be thought of more as understanding the failure modes of a system, where the application is behaving as expected, whether it is broken, what's going on, what's maybe slow. Observability is having more visibility into the system as a whole, not just knowing you have a problem, but understanding why it's happening, and hopefully also with a path to resolution. The sort of technical control theory definition says, in control theory, observability is a measure of how well the internal states of a system can be inferred from knowledge of its external outputs. So that means you can't always predict every single potential failure, which is something you can monitor for as a known problem. So observability helps to combine the outputs your application produces, which is instrumentation data you gather about your app, and you correlate it across all your different services. So these are the different outputs correlated with better debugging, good testing, and this is all built into your software development lifecycle. I like to think of it as being able to look at the big picture from the outside looking in. And this is the idea, is to be able to help work out everything that's going on in an application and hopefully being able to then spot the sort of unknown problems. So observability consists of 3 pillars: metrics, logs, and traces. And importantly, providing the contextual linking between these 3. So metrics gathers the numerical data about things you want to track for your application. Think of request rate or error rate, or also business metrics such as number of orders placed or payments received. Logs are then time-stamped records of events. Something happened at a particular time, a failure, an error, something informational, maybe a state change, and logs may have the metrics included within them. And then traces are a single user or transaction journey through a number of separate applications or parts of a single application. For example, if I'm alerted on a metric, I should be able to see the associated logs and traces with a few clicks and easily navigate between the different components of my application. If I can do that, I can spend less time working out what's actually wrong and then have more time fixing the problem. So contextual linking is the observability thing that interconnects all these 3. So they need to be correlated together to bring better visibility. Failure is something that is embraced. It's not just something that's monitored after the application is built, but the failure modes are actually designed as part of the application during the software development lifecycle. You need to make sure that you're collecting, first of all, enough data to actually understand the system. If data is missing, you could have gaps in your visibility. Debugging is super important part of observability, using the data you collect to help with quick troubleshooting. And realistic testing also often happens in production, not just in isolated test environments. As often smaller components are being released, more often testing these smaller changes in production becomes super important. Things like canary testing can be used when you target initially just a small portion of your users. They try out the new code and then test everything's behaving as expected, and then gradually rolling out the change to more and more users while still testing things are behaving. If the application behavior isn't as expected during these incremental deployments, for example, some metric you're gathering says, as you ramp up, things are getting slow, you can roll back the incremental change automatically and safely. So AWS has 2 main services to help with observability: Amazon CloudWatch and AWS X-Ray. So CloudWatch, I'm sure you're familiar, is a service that collects monitoring and operational data in the form of logs, metrics, and also events. It gives you a nice unified view across your resources, apps, and services. And also you can set up alarms to alert you if something important is wrong or even right. You can visualize your logs and metrics side by side. You can take automated actions and what appears in your logs or traces. And then so X-Ray is the AWS tracing service. And so this helps developers analyze and debug production applications. And it's particularly helpful for those built with multiple distributed components. So you can see a transaction or a user journey as it travels through a whole bunch of different components. CloudWatch and X-Ray have a number of services and features to help you with observability goals. They allow you to collect the logs and metrics. Then you can monitor the collected data using dashboards and alarms so you can see what's going on and view history to spot some trends. You can also then act on the data with alarms. If an alarm is fired, either based on static values or some anomaly detection, you can then send an alert or run an automated task based on an event, and you can also do canary testing. And then you can also analyze your logs by running queries for visualization or analytics, or use high-level services like Service Lens to analyze across your applications, which I'll also have a look at today. And of course, this all happens on AWS at massive scale. Yes, 1 quadrillion, which is 1,000 trillion metrics observations each month. There are trillions of events each month and 1,000 petabytes of logs ingested. CloudWatch runs monitoring for all of AWS and Amazon.com, as well as many of our customers. So a lot is going on in the observability and monitoring space at AWS. But, CloudWatch and X-Ray are not your only options. We have a really broad partner ecosystem with some amazing monitoring and observability products and features. I would love to have the time to go through all of them and show you what they can do, but just like a Lambda function, sorry, I can't go on forever. Some of the partner integrations offer a lot more than monitoring or observability, and are able to help with maybe some integrations to other parts of your stack, which could be useful. They can also fit well into many aspects of your software development lifecycle. Developing serverless applications then also doesn't have to mean you can't use your existing tools if you rely on one of these partners. So I really suggest you take a look at some of these partners. X-Ray and CloudWatch are out of the box, are simple to get going with, but these monitoring partners may have something more for you and help to connect with other parts of your application. So heading into a bit of CloudWatch, next we're going to talk about what metrics you have available without even doing anything yourself, other than obviously building your application. So CloudWatch comes with a number of standard built-in metrics. These are automatically generated when you use Lambda, API Gateway, and many other serverless services. Lambda has 13 built-in metrics covering various invocation, performance, concurrency metrics, so you can easily see how many functions are executing, how long they're taking, what invocation errors you may be getting. There are also many new concurrency metrics for seeing how many functions are running at the same time. API Gateway REST APIs gives you 7 metrics showing how many API calls you're receiving. You've got things like error counts, cache details, and the newish HTTP APIs and WebSocket APIs have I think 6 built-in metrics. So remember, these are automatically generated, so you don't have to set anything up yourself. We'll take a look at what they look like in the console shortly. I'm going to show things for a demo application which is called Fresh Tracks. This is a web-based, entirely serverless application for uploading and viewing your mountain ski or snowboard adventures. My colleague, who's an awesome skier, Ben Smith, he wrote this application. And so, yeah, it's a really cool sort of way, a nice way to be able to show some of observability. So just to go through the architecture. Amplify Consol hosts the front-end code, which is stored in S3. It manages the URL and has a built-in CI/CD pipeline. When code is pushed to GitHub, in this case, you can use other code repositories. In the Fresh Tracks repo, new builds and tests are done automatically, and the updated application is deployed if everything looks good. Authentication is managed by an external service, Auth0, and there's an API Gateway, REST API, which allows the front-end client to upload the track GPS files, and these are in GPX format. This is directly to S3 using pre-signed URLs and a Lambda authorizer. When the track lands up in S3, an event bridge rule kicks off, and this then kicks off the step functions, express workflow, which processes the GPX file data. Stores the data in DynamoDB and then notifies the front end via IoT core that the track has been uploaded. The client then can retrieve the list of previously uploaded tracks again via API gateway. This is coming from DynamoDB, and select an individual track to show the GPS route on a map. Believe me, I was super happy to be involved. We did some extensive on-mountain research in the development of this application. Ben, Rob, and I had some awesome days on the mountains. These were before COVID days when we could get out. So let's take a look at an actual application. So what we can do with the app with Fresh Tracks, we can upload some GPS data files for the ski or snowboard runs we've done to S3. And the files then get processed as a workflow by the serverless backend using the step functions and Lambda, as I mentioned, with metadata stored in DynamoDB. The front end's now been updated via IoT Core, and we can go and view each uploaded file, which is a track, and see the GPS data plotted on a map. So if we go then jump into the AWS Management Console and go to CloudWatch, we can see a number of resources that Fresh Tracks uses. I can select an individual service to view the automatically generated metrics. So here I can click on Lambda. I can also click on, for example, API Gateway. And I can also select a cross-service dashboard to see the important metrics for all services in my application in a single page. So it's really easy to get a basic view of your application without having to do much by just viewing the automatically generated standard out-of-the-box metrics. So let's now take a deeper look at logging and structured logging in particular, and see how this can be helpful. So CloudWatch Logs generates logs for a number of AWS services. For API Gateway REST APIs, you can have execution logging and access logging with two levels, error and info. You can also choose to log the method request and the body content for deeper troubleshooting. HTTP, API Gateway REST APIs, logging, you can either log globally in the stage, or you can overwrite the settings for individual methods. There's also CloudWatch logging available with the new HTTP APIs and WebSocket APIs. For Lambda, you can log directly from within your application code using a standard debugging console.log statement, or whatever equivalent is for your function language of choice. This is useful for logging some basic request information, and certainly useful when you're developing. You can also create JSON structured logging, use either the put metrics data API call or the new embedded metrics format. And I'm going to cover this more shortly in more detail. And this also then includes additional information, including some of the function invocation info. So once you have your logs being created, you can do a number of things. You can filter them, you can create metrics from them, or even ship them off somewhere else for analysis. So looking a little bit more at basic structured logging, here's a standard message format. So this may be part of an event your Lambda function is working on in your application. It's got a number of fields. You can then do your language equivalent of console.log in JavaScript or print for Python, and send this message to CloudWatch Logs. This gives some basic logging information and appears just as a text line in the logs, but it's difficult to correlate, and you often had to build complicated systems to then extract real metrics from the logs. So to help with this, AWS has released the embedded metrics format to publish logs using a specific format. This allows you to embed custom metrics, which may be part of the event payload, alongside more detailed log event data, which includes the invocation information. These then get automatically exported as metrics without the need for any additional processing on your part, and they can then be consumed for dashboards and alarms as well. And there are open source libraries available for Node.js and Python. So here you can see the actual structure of the JSON EMF log format here. You can see this includes the Lambda function invocation information, along with a metric, in this case, time in a specified unit, milliseconds. This log with the included metric will then automatically be exported to CloudWatch metrics, so you don't have to ship your console.logs somewhere else, or then have a whole other process to extract and generate the metrics yourself. Now, one thing to mention is the embedded metrics format is more verbose than console.log messages because it's got more information. It's certainly more useful information, but it will impact your CloudWatch logging billing. So make sure you're managing your log size and rotation properly. This is a recommended best practice anyway. So staying with metrics, there's also often a need for custom metrics, application, business, and operations metrics. As helpful as they are, the built-in metrics are often enough. You likely need more visibility into your application, and not just at an infrastructure or application level to get that observability you are looking for. You may need to track your business and customer metrics. For example, how is your application performing against business goals? Are you generating the revenue you need? Are you getting enough people signing up for your awesome service? What's the customer perceived latency? Are customers uploading the number of tracks you expect? Operational metrics are also important for observability. How often can you safely deploy? How long does it take to recover from a failure? How often are you having to wake up your developers, for example? And then what about other Lambda errors like caught exceptions, which are not counted as errors? How are you handling them? What if you want to create metrics for a particular category or environment, what's called another dimension? This is why you need custom metrics. These are the metrics that are specific and important to your application. And you can generate custom metrics by instrumenting them in your code. So let me just switch over to VS Code and look at the actual FreshTracks application. We can see here one of the Lambda functions which processes the GPX files. We have added the embedded metrics format as a package dependency, and we create a metric scope and then add a custom dimension and also a namespace for the application, which we've set as 1-FreshTracks. We can just generate custom metrics for anything. We may want to track a function cold and warm starts if that's important. And we can add properties and metrics to it. In this example, we've chosen to create a custom business metric, which tracks each ski or snowboard track updated. So in FreshTracks, once we upload a number of tracks within the application, we head back to the CloudWatch console metrics section, go to FreshTracks, and we see all the custom metrics that have been generated for this application. We can graph, plot to our heart's content. Here I've just plotted a quick line graph for this application to show the sum of all tracks uploaded over the past 5 minutes. And I could also decide to display that as a number rather than a graph if I want. So anything available in CloudWatch metrics, what you've used for the standard metrics, you can now plot and create anything for your custom metrics as well. We can also use CloudWatch Insights, which is an interactive log analytics capability for CloudWatch Logs. This allows you to search and visualize data based on anything in the logs. So in this example, I've just picked the sum of all tracks uploaded, which is our custom metrics. I select the Lambda function log group and then run the query for the sum of tracks uploaded to see the results in this over time in this example. But we can also do way more complex queries, even looking at built-in platform metrics. Say, in this example, looking at the most expensive Lambda executions. This query creates a report which gets the request ID and then also retrieves and sorts by the build duration and displays the first 100 results. You could use this to find out any Lambda functions across one or more log groups that are taking longer than expected and maybe investigate further for performance issues. You could also use this to know where you can look first to save costs by finding the most expensive Lambda executions. Or another way to use CloudWatch Insights is to search all the log groups for a single function or set of functions and maybe find the most recent 100 errors, for example. This could help troubleshoot and pinpoint function errors without having to navigate to each function log group manually, which you can imagine would be a pain. CloudWatch Logs has also recently added saved queries for insights. This allows you to save and organize queries in folders and then easily run them again, even for a different purpose by another team or for another application or runbook. So CloudWatch Insights gives you really some powerful querying and analytics abilities to get insights into your logs. Something you also may want to think about is creating a shared observability module for your application code. In the FreshTracks example, I've instrumented a single function as an example, but it makes sense to write some of your logging, metrics, and tracing calls in a way which can be shared between multiple functions. Lambda layers is a great way to then share this module between multiple functions or even multiple applications. The way it works is you zip up the contents of your shared observability components and upload it as a Lambda layer. They can be managed and versioned centrally, and you can include up to 5 layers for a Lambda function, one of which can also be a custom runtime if that's something you need. So we have all these logs and have some standard and custom metrics set up. We would also like to alert on them to know if something is going wrong, also to find out if we've hit some kind of business number that's interesting. Remember, alerts don't also have to be for issues. They can be alerting on anything, even a business outcome that you want to know about. So, for a simple example, let's set up an alarm to alert on tracks uploaded. I create an alarm. I select the metric from the Fresh Tracks application, which is the custom metrics already set up. I change a statistic to alert on the sum, and then select the static threshold to alert when there are less than 5 tracks uploaded over 5 minutes. Then I select an existing SNS topic for alerting. I've set up one already, which emails me when the alerts get triggers. I give the alert a name, and I can see the alert has now been created. So when the alert is triggered, I can pop over to my email client, and I can see here I have been notified. So in this example, this was a business outcome. If normally my application is pretty busy and less than 5 tracks were uploaded over 5 minutes, I know something is wrong in my application. I may not know yet, but at least that's the business outcome I can track and start to further look into it. So you can also configure alarms via CloudFormation. Here's an example of an API gateway alarm alerting on P99 latency if it's more than 1,000 milliseconds. This means you can set up your alerting as part of your application code. And this is also part of what observability is about, building in ways to understand, view, and also be notified from your application as part of your application development, tying those different parts together. Alarms can also be created using anomaly detection rather than static values. The way this works is if there's a discernible pattern or trend in your application, say you do food delivery and you get a big spike on Friday night, anomaly detection looks at past metric data and uses machine learning to create a model of expected values. You can then alert if the metric falls outside of the band of normal values. So in our food delivery example, on a Friday night, you wouldn't get alerted for the usual spike in the same way as on a Wednesday lunchtime when orders may be far lower. So onto the third pillar of observability, which is tracing. So we've mentioned before, but X-Ray is a distributed tracing solution from AWS, and which provides an end-to-end view of requests as they travel through your application. And it also nicely shows a service map of your application's underlying components. X-Ray collects data about the requests that your application serves, which helps you understand how upstream and downstream services may affect workload health. You enable X-Ray for various AWS services, including serverless ones such as API Gateway, Lambda, SNS, SQS, and AppSync. For Lambda, you enable X-Ray and then instrument your application code to add tracing data. For API Gateway, X-Ray talks directly to, for API Gateway, X-Ray talks directly to X-Ray the service, as well as inserting a tracing header into HTTP calls, which can then follow your Lambda function, so you know which API Gateway call is associated with which Lambda function invocation. X-Ray receives data from services as segments, which you'll see shortly. Segments for a common request are then grouped into traces. Segments can be further broken down into more granular subsegments. And then you can also add some custom data key value pairs with annotations and metadata. So these are custom descriptions you can add to your code. Say you want to capture a payment ID generated by a third-party service and add that to all the segments as it flows through your Lambda functions. Traces can also be used to help with filter expressions. So you can add your custom data to a trace. The custom data may not have been generated by some part of your application, but you could send a customer ID or a payment ID through the whole stack of your application tracing to help you correlate it all together. And also, the X-Ray team is working hard on bringing X-Ray to even more services. So, keep an eye out there. I'm sure there are going to be some new goodies soon. Enabling X-Ray is actually a super simple process. In the AWS console, for a Lambda function, you just need to basically check the box, view traces checkbox in the Lambda configuration. And for API Gateway REST APIs, you enable X-Ray per stage. You do need to make sure you have IAM set up to write to X-Ray. This is done automatically if you enable in the console. Once X-Ray has been enabled, this will then automatically start to collect tracing data for your functions and APIs for the subsequent requests. The AWS Serverless application model is AWS's purpose-built serverless abstraction for CloudFormation. It's SAM, which we call SAM, is a great framework to use infrastructure as code to develop your serverless applications. And with SAM, you can super simply set up X-Ray. You can either enable tracing for individual functions or REST API stages, or even easier, with just 2 lines of code, enable X-Ray for all functions and REST APIs in the global section, as you can see here. Okay, just 2 lines of code. I did say, but you will also have to add the permission for X-Ray put trace elements and put telemetry records to your Lambda's execution role in your SAM template. So to then add even more information to X-Ray, you can instrument your code. So jumping back into VS Code, we can see the function to write data to DynamoDB. What you do is you replace your import of the standard AWS SDK with an X-Ray version, which then automatically traces all AWS calls to other services. Here we can see the put call to DynamoDB will then be routed through the X-Ray SDK version. And you can also add your own subsegments, annotations, metadata, maybe such as I was mentioning before, the customer ID or payment information. This is where you would add that further tracing information. So heading to the X-Ray console, we can view the service map for fresh tracks and select the Lambda function that this time reads from DynamoDB. We can then go straight ahead and I can view the traces and drill down into the duration periods of invocation. We can see the calls through API Gateway to the Lambda function and the DynamoDB query within the Lambda function. So we can see an end-to-end trace of a single transaction through our application, showing the time spent literally in milliseconds or seconds for each part. If you had calls to other AWS services supported by X-Ray, you would also see them here. This is where you would see the segments and subsegments if you created them in your code. And if I had set up annotations and metadata for any custom data we wanted to capture, we could click on a segment or subsegment here and view it directly in the trace information. So the last part of the presentation is how do we bring this all together? How do we use the instrumented data we are gathering from logs, metrics, and the traces? Well, at reInvent 2019, we announced Service Lens, which is specifically for this. It ties together the CloudWatch metrics and logs, as well as the traces from AWS X-Ray. It does this more closely to give you a complete view of your application and their dependencies. This enables you to more quickly pinpoint performance bottlenecks, find out what's wrong, and have a better idea of how users may be impacted. Heading into the CloudWatch Service Lens console, we can have a look and see the service map, which is automatically created from the X-Ray traces. We can hover over a node. This time we'll choose API Gateway and see some immediate information. We can then select a node and see more API metrics. And then straight from here, we can jump directly into the traces and see the response time distribution of the traces. I can select then a GET request and then see the whole trace path again through API Gateway, Lambda, and DynamoDB as we did before. This is similar to the views we had seen before directly in X-Ray. It's basically using the same underlying data, but it's certainly further integrated within this console. And so Service Lens really makes it super easy to jump between all the metrics, logs, and traces, and just makes it easier to have more observability for your application. Something else we haven't really covered, but it still fits into the observability feedback loop, is testing. Remember when I was talking about how smaller components being released more often and how to think about testing in production? Well, canary testing is testing out a new part of your app when it's rolled out to a small subset of users, or even doing testing with no external users yet, maybe just trying out on your internal staff. Well, CloudWatch Synthetics is a service to help with this testing, to monitor application API endpoints more easily, and it's currently in preview. You can create canaries to run tests for things such as availability, latency, or even things like dead links. Synthetics can let you know when it finds a problem, even when you don't have any customer traffic on your application, and you can discover issues before your customers do. So certainly worth taking a look. So we've been through a lot, certainly covered a lot. We start with Werner Vogels' quote, everything fails all the time, which I really think of as sort of the observability call to action. And certainly monitoring is evolving. With serverless, there's much less infrastructure to have to monitor yourself. You don't have to monitor so many layers of the stack. That becomes AWS's responsibility. You get to focus more of your time understanding your application and business, likely spread across a number of distributed services. I covered what observability is, how it's derived from control theory, and then all about gathering the right data so you can observe the inner workings of your application from the outside. Then went through how CloudWatch and X-Ray can be used, along with a number of very helpful partner solutions, which I really encourage you to take a look at. We looked at the AWS service provided standard metrics and dashboards. I then looked at more detail for the ones for Lambda and API Gateway. I then went through why you need to also include custom metrics, and why business, customer, and operational metrics are also very much part of observability. As I mentioned, you can do this by instrumenting your own code to provide more useful logs, and then also using the embedded metrics format to generate metrics automatically from structured JSON logs. These can then be used to get great insights into your application with visualizations and queries, and answer many questions about what's going on in your application. And then covered creating your own alerts. And then I looked more at how X-Ray can be used for your end-to-end tracing. How you can trace a single request or customer journey through a number of different services, which really helps with understanding your application and also troubleshooting. And finally, I looked at how Service Lens can be used to more easily hop between metrics, logs, and traces. So this all helped to round out how I like to think of observability, getting the data you need and being able to quickly act on it. So yeah, really appreciate your time today. I'm super happy to take any questions you may have in the Q&A, or if you are watching this later, you can certainly get hold of me on Twitter at Julian_Wood if anything is on your mind. So yeah, thanks so much for joining us, joining me here and all of us today at the London Serverless Meetup. Yeah, happy to share any questions. I think Ben and Ant have some, hopefully some questions from the chat.
Yep.
Far away.
Well, thanks so much for an amazing talk, Julian. We had a couple of questions come through. A few people wanted the source code, which was shared out. And we have a question, is there a way to log more, so sort of debug and tracing for only a specific user when troubleshooting? So he can think of how to do it by coding a Lambda specifically to do it, but he's not sure if there's a better approach for that sort of use case.
Yes, I mean, a particular user would have an individual trace from your front-end code. So you could add a custom metadata for a customer number, for example, so that you could use, for example, to then group all traces based on a customer. So you know, somebody is logging on to your, or logging on, or even using, you know, logging on would be super easy if they are logging on to your application and they maybe have a cognito user ID and something using a JWT token, you could pump that back up into the metrics and use that to correlate an individual user path through your application, even though they're making multiple traces. So yeah, that's certainly an option. You can do that.
Awesome.
Back to the first question about the code. Yeah, silly me, I should have put a link to that. Literally just search on GitHub or for serverless fresh tracks, and it's on the AWS samples GitHub page, and all of the code is there for that application.
Sure, and Ant's already shared the link out in the chat as well, so you can access it directly.
Excellent.
We have another question about SAM. Is there a way to manage existing lambdas and its triggers and aliases exported from a SAM template? The exported template deploys new resources when executed.
Yeah, that's you can use existing resources within the SAM template as an external thing. Normally, often that can be the case if you, for example, have a DynamoDB table, or you have an existing state somewhere in S3. You don't want your SAM template to, need to create DynamoDB or S3 as well. I don't think you can, in that specific example about using an existing Lambda function, but just updating the triggers in a SAM template. I would think you would need, if you were going to use SAM to manage, SAM would need to manage that individual Lambda function. And yeah, I don't think you can just have an existing Lambda function and somehow just edit the triggers for that. You would need to do that. Saying that, you can also manage CloudFormation natively within SAM. So, okay, Lambda is one kind of thing, but if you do have existing CloudFormation resources, you can just bring them into SAM directly as an existing resource.
Sure. And then one final question on X-Ray logs. Currently, the traces in X-Ray are often quite short because it doesn't support making long traces over services like SNS and SQS fanouts. Is this something that will be added in the future?
As I said, the X-Ray team is working super hard, because that is one of the issues with any observability tool, and particularly tracing, that the big power in tracing is having the sort of end-to-end visibility. And so you want to enable X-Ray for as many services as possible. But yeah, unfortunately, today there aren't services that X-Ray supports, but X-Ray is getting a lot of love and attention within AWS. And yeah, I would expect in the future, we will be rolling out X-Ray support and also longer tracing information to more services.
Awesome. Well, thanks so much, Julian. It was really great talk, and thanks for asking the questions at the end.
Yeah, absolute pleasure. Yeah, I'm at Julian_Wood. And so, yeah, any other information you want, we've also got just so to let you know some other information, our developer advocacy team for serverless at AWS has grown hugely over the past year and a half. So we've got some excellent people cranking out as much content as possible. And some of that's going to be code, some of that's going to be video stuff, some of that's going to be blog posts. So yeah, we're on LinkedIn, we're on AWS Serverless on the YouTube channel. Every quarter we publish some in case you missed it posts, which have all the links to everything we're sharing. So yeah, that's literally half of our job only as well. Just to mention is creating content for people to use and enjoy our services better. But also the very important part of it is we very much want to get feedback from you. We're very into fostering community, and we're very interested in listening to our customers. So if you know things that you need or want from anything AWS services, please get in touch. We would absolutely love to pass your requests on to product managers, or see what we can do ourselves and make your serverless life even better. So thank you very much. Have an awesome day.
Thanks so much. Before we jump into our next talk, I just want to say a quick thank you to our sponsors, Theodo and Senzo, for helping to organize this event. And our next talk is Jeremy Daly talking about building resilient serverless systems with non-serverless components. So without further ado, Jeremy, do you want to take it away?
Yes, thank you. First of all, thank you for having me. I appreciate that. I'm going to get my screen shared here. Okay, so this talk is building resilient serverless systems with non-serverless components, sort of a mouthful, but the idea is that no matter what we do as serverless as we think we can get, we are eventually going to bump into some components that aren't going to scale quite as well. So make make sure I can do this. All right, so my name is Jeremy Daly. I'm an independent consultant. I work with a lot of companies in the cloud right now that are building serverless. I've been doing this for a very, very long time. You can probably see from my picture to now, my beard is even grayer. I started working with AWS in 2009. And then from there, once Lambda came around in 2015, I started using that pretty heavily and got into the serverless stuff. I do have a blog at jeremydaly.com. I write quite extensively about serverless. I also have a whole bunch of open source projects, do some speaking. Sign up for my newsletter that I publish every week on Tuesdays. It's a wrap up of all the things that are happening in the serverless space, mostly around AWS serverless space. I also host a Serverless Chats podcast, and I have a new web series coming out called the Serverless Spotlight, which will be pretty cool. So stay tuned for that stuff. I'm also an AWS Serverless Hero, which is a great program that AWS has. Ben's a hero, Ant's a hero. It is a great program that just allows us to really work with the teams at AWS and to push, to get feedback from the community and to push that into the product roadmap. So it's a great program that if you're doing a lot of stuff with serverless, you should definitely look into because it is it's a lot of fun and you meet a lot of great people. Okay, so today we're going to start by talking about what is resiliency and what is serverless. You're on a serverless, meetup, so I'm sure you know what serverless is, but we're going to put it into the context of what I mean by serverless so that we can get a framework for what non-serverless would be. We'll talk about working with less than scalable relational database systems. We'll talk about using unreliable APIs, managing our API quotas, and then decoupling our services. And then finally, we'll finish with talking about a couple of other non-serverless components that we may need to deal with. So first, we need to talk about resiliency. Julian mentioned a little bit about this. The definition that I like to use is that it's essentially the ability for a software solution to absorb a problem, right? So that means that not the whole entire system is going to be running. Maybe something goes down, but the system would still have some acceptable level of service. So this is really not about preventing failure. This isn't about reliability. This is really about understanding how we can gracefully deal with partial failures within our system. And when you start talking about distributed systems, you're going to have a lot of partial failures. So what does it mean to be serverless? These are the standard things we usually see: no server management, flexible scaling, pay for value, automated high availability. But the other thing is that there are lots of configuration and knowledge of cloud services that are needed. If you just watched Julian's talk, you notice that there were a lot of different components that were mixed in there, and you really had to know how to instrument them to do the cloud logging and some of those other things. So that's something that you need to think about when it comes to serverless, and then also highly event-driven. So essentially, anything that is going through these applications mostly is going to be driven by events. It's not like just having something up and running. Of course, I think all the serverless people listening mostly know that. But today's talk is going to focus mostly on the idea of flexible scaling. So let's look firstly at a couple of services that AWS considers to be serverless. And yes, I did put Kinesis in there, because I do consider that to be serverless. So the serverless things on that side are things that are completely managed for you, and you don't have to worry about the scaling characteristics of it. You don't have to do any capacity planning. For the most part, those will just scale as you throw work at them. Then there's this other category of managed services. So these things are managed for you. You don't have to go in and install updates to Amazon Elasticsearch. You don't have to worry about Elasticache, that be coming out of date. But you do need to do some capacity planning when it comes to these things. And then finally, there are the things that are clearly not serverless. So this would be anything that's running on EC2, and then things like Kubernetes and Docker and Kafka and MongoDB. These things are definitely not serverless. So just keep this sort of framework in mind as we talk about some of these different components, and that'll sort of get you thinking about where you need to start thinking about capacity and where you need to start managing workloads and mitigating workloads so that you don't overwhelm some of these other systems. So an important thing to remember with the cloud is, as much as we think things can scale infinitely, everything has limits. Even with fast, we still have reserved concurrency. We have function timeouts. We have memory limits on that. We also have network throughput that can be minimized, or that can be a bottleneck for certain things. And with some of these managed services and some of these other serverless services, some of these components are better than others, but the most important thing, and I guess the best advice I could give you when you're looking at a new service, is to know what the service limits are. And that's clearly published on all the AWS documentation. If you're using some other provider, Azure or Google, those are published there as well. So it's important that you know what the limits of your application are so that you can design your application around those limits. So if we look at a simple serverless web service, this is sort of the iconic, this is in a perfect world, everything would be perfectly serverless. And we have this really highly scalable API gateway that connects to this highly scalable Lambda function that connects to this highly scalable DynamoDB. And that's great. But if you remember the Dire Straits song from, I think, the early 80s, that I want my SQL, and developers are just not ready to throw away relational databases and go full to NoSQL. Not that they can't anyways. There's plenty of applications that still need to use relational databases. Anything that's analytical, things like that, are going to need that service. So if we take that same simple web service and we have our two highly scalable components, and then we throw in something like RDS. Even though RDS is scalable, it's not that scalable when it comes to competing with something like Lambda or API Gateway, unless we just throw a whole bunch of different machines. And so this is sort of the not so, or the simple not so serverless web service. And part of the reason is because relational databases and functions as a service don't really play well together. And that's because the way that the concurrency model works with a Lambda function, for example, is that it just creates a new container for every single concurrent function or invocation. So that means it has to create a new connection to the database. So you can't utilize connection pooling right out of the box, which means you then have a limited number of database connections available. And then whenever a Lambda function gets recycled, which might be after 15 minutes, might be after an hour, it might be after 10 seconds, that connection to the database sometimes takes a while to clean itself up. And therefore you get a bunch of zombie connections. So there are a number of different ways that we can manage database connections to our RDS clusters. One thing we can do is we can mess around with the database itself and increase the max connection setting. This can be a problem because most people are used to connection pooling. They don't see the effect that too many connections will have on a relational database. But if you have too many open connections to a relational database, it often spikes the CPU. It's very CPU intensive, and that can often cause issues. You put too many connections and the database can't handle it, and then you're going to potentially throttle everything else around that. You could try limiting the concurrent execution. So that means we could say, hey, our Lambda function can only have 500 concurrent connections. But if users start hitting up against those limits and they start getting too many request errors, then that's not going to make them very happy. We could do things like lower connection timeouts. That's one of those things where we say, well, if the zombie connections kick in, then we'll just make sure that they expire after 2 minutes or after 5 minutes or whatever it is. That's not always a sort of a hope and pray sort of strategy. You can limit connections per username and play games like that. Or you could close connections before the function ends, which is a terrible idea because the bootstrap to set up a new connection into something like MySQL, for example, it just takes too long. So really, all of these ways are terrible ways to do it. So let's look at some better ways that we can do this. So the first step is we could implement a good caching strategy. We don't need to be connecting to our database all the time, especially if we have a read-heavy application and there's not a lot of data changing. It's very common to use a good caching strategy so that we can minimize the number of connections to the database. And even if we're using a lot of connections, but we're not making a ton of queries, that can help alleviate that. We can buffer events for throttling and durability. So if we have a high write frequency to our database, then we can use throttling, and I'll show you how we can buffer events so that we can minimize the impact on the database there. We can utilize a proxy service. Some people are probably thinking about RDS proxy. That is something we can definitely use, and we'll talk about that in a little while and why it's good, and also where some of the limitations are there. And then we could manage connections ourselves. And for everyone who's thinking, well, what about RDS proxy? Again, we'll talk about that. There are plenty of reasons why we might need to manage connections ourselves because of the type of database that you're using. So these are all better ways that we can deal with that. So let's dive into some of these and look at them. So if we look at our standard, I guess not so serverless web service, and we put our RDS cluster there, rather than connecting directly to RDS, we're just going to throw Elasticache in there. And if we're using RDS, we're going to be in a VPC anyways, so we're going to have Elasticache available to us in that VPC. And what we do is we check Elasticache. If there's a hit, then we respond back. We never even make a connection to the database. If we make a request and this time we get a miss, then what we're going to do is we're going to contact the database. We're going to download whatever data that is. And then Elasticache is not a write-through cache. It's not like DAX, for example, for DynamoDB. So we are going to have to write that data into the cache, and then we can respond back to the client. And now we've got that data saved. So just a couple of key points. Again, this is a standard caching strategy. Do need to make sure we only connect on misses. So especially if it is a high read application or a high throughput read application, then it's possible that you get Lambdas spinning up all the time. If those Lambdas are warm and they're constantly hitting the cache, and all that data is now in the cache, you've got a nice warm cache, there's a possibility that you will minimize dramatically how many times you have to connect to that RDS instance. And it's possible the Lambda invocation itself might never need to connect to RDS. We want to make sure that we set our TTLs appropriately, the standard caching stuff. We don't want them to last too long. And we also want to make sure we include the ability to invalidate the cache. So if we do have another Lambda function that updates our RDS cluster, we want to make sure we do some cache busting in there so that we delete that key so that the next request will rehydrate the cache. Another thing here is that, a lot of people don't like the idea of putting caches in front of databases to mitigate the stress on the database. I think that is sort of a standard thing where you do want to make sure that you size your RDS cluster appropriately. So if you do expect to have 1,000 concurrent connections, don't set it to 200 max connections on your database and just hope that your cache will handle that for you. You still need to make sure that that your database could handle it if your cache was to go down. But again, these are just good ways to sort of mitigate that and avoid, potentially overwhelming your database. The other thing that this does is it does add a bit of resiliency in there, that if you've got a 90% warm cache, for example, and your RDS database goes down, or the backup goes down, or it's in the process of rerouting via DNS or whatever it's doing in order to get it to fail over to a different region, for example, there's a possibility that 90% of your requests could be served from the cache while that database is not available. And again, you can design your application to serve back a message saying, we're having some issues, but hopefully it only impacts a very small number of requests. So the question, though, when it comes to something like writing directly into a database, a relational database, is whether or not we actually need feedback from that database immediately. So there's two types of communications. Everyone's very familiar with synchronous communications. These are the blocking requests. That's I make a connection to the database, I wait for it to respond, I get that data back, and I respond back to my API. This is a standard way that we've been doing web applications for a very, very long time. With the advent of not just the advent of serverless, but a lot with the advent of microservices, this idea of non-blocking requests or asynchronous communication has become much more important. And I'm sure most people are probably familiar with this, but it is something that's relatively, it's not overly common if you were just in the web development space. So what this essentially means is that rather than us waiting for something to respond, we just need to be able to make a request to it, and then we basically disconnect, and then we can go about our business, and then we wait for something else down the line to tell us that request is completed. So this is a great way to minimize the round trip, reduce the latency of something like an API call, because that way we don't have to actually wait for the database to respond. And even better, if the database isn't available, then we can still provide a pretty good experience for our user, depending on what it is that we're trying to do. So this works really well for high volume write things, something like a webhook, for example. And what we would do here is we would have our standard API gateway and Lambda function, stick an RDS cluster somewhere there. But rather than writing directly to that RDS cluster when that post or that put request comes in, instead we're going to write the data into an SQS queue. Now this is a asynchronous request. I put it in quotes because it's technically a synchronous request that the SQS queue says, yes, we've got it. But essentially what you're doing here is you're passing off that message to the SQS queue. Once the SQS queue says, hey, I got it, it'll send an ACK back. And now your Lambda function can respond back to the client and say, I got your message. If you're querying a database and you're looking up a client or you're looking up a product or something like that, obviously this doesn't work. But if you just need to make sure data gets written into the database, then this is a great way to add that durability by writing it to an SQS queue. SQS queues are extremely durable. And they are very, very lightweight, so they can handle tons of requests, much more than your RDS is going to be able to handle. And so what you then do is throw another Lambda function in the mix here that is attached to the SQS queue. It uses that as the trigger, and you can limit the concurrency now to match whatever your throughput might be on RDS. So we talked about lowering your concurrency as a possible way in which you would want to mitigate the number of transactions to a database. Typically, that's a bad idea with a synchronous invocation, but with asynchronous, it doesn't really matter, right? Because we're stacking these things up in a queue. So we can limit that throughput so that we don't overwhelm that database. Now the Lambda function will pull the SQS queue. This is a synchronous request, so that we'll go ahead and write the data to RDS. RDS will say, hey, I got the data, or no, I didn't. If it says I got it, then it tells the SQS queue to remove it from the queue. Your data is now hardened in the database. And if you wanted to, you could fire off some sort of an event or something like that from that throttled Lambda function that says that this file has now been processed or this record's been processed, and you could do something down the line there. If it fails though, so let's say that it can't connect to that RDS cluster, then we can tell the SQS queue, hey, it failed. And depending on how you set up your redrive policies and things like that, it'll eventually write that into an SQS DL queue, which basically takes it out of the main queue, but then gives you the opportunity to go and actually save that, so you don't lose any of that data. So a couple of key points here. Again, SQS adds a tremendous amount of durability, right? So if your database goes down, it's much more likely that your database is going to go down and your SQS queues are going to be up and running. So that way, if there is some sort of failure, you keep that data. Those throttled Lambdas will reduce that downstream pressure. If you think about this, let's say you have an application that sends out emails, and you send out 100,000 emails, and everyone's opening their emails, and you've got all these webhooks coming in saying somebody opened it, somebody opened it. 99.9% of the time, your RDS cluster does not need to be scaled up to handle 100,000 requests within a few seconds. But using a service like this, or using a pattern like this, then that SQS queue can fill up, and it might take a minute or so for it to work through all of those, all that backlog. But it is a good way that you can keep your costs low without having to provision extra capacity for your RDS cluster when you don't need it most of the time. And then again, as we mentioned, those failed events do get stored for inspection and replay. Now, what happens all the time is if you have that data that gets written to a database and there is some invalid character there, or there's something's too long and you didn't truncate it in your Lambda function, or you didn't truncate it before you wrote that to the database, that record's just going to fail. And unless you're logging it and doing something like that, you're going to lose that message entirely. This way, if that happens, then it's just going to fail, and it's going to write that to that DL queue, and we're not going to have to worry about losing that message completely. And then often you can go back in and you can fix it and figure out why exactly your Lambda function didn't work, and then you could always reprocess those events if you needed to. Now, something interesting here, you don't actually need this Lambda function if you are just writing data straight into SQS or straight into DynamoDB. Eric Johnson has what he calls the storage first pattern that writes it right into DynamoDB. Those are all great ways to do it. You can do that by using what's called the service integration with API Gateway. You can only do that with the REST APIs right now. You can't do it with HTTP APIs yet. But this is a good way to do it, because you don't really have to. You can do very, very basic image, very basic, not image, sorry, very basic like a structure, detection to make sure that it meets certain criteria, that it's shaped correctly before writing it into the SQS queue. But then if you need to massage the data or change things or do lookups or anything like that, you can do that all in that Lambda function in the throttled one when it downloads the data after the fact. So just a way that you could save a little bit of money and then potentially introduce one less or one smaller piece of code or less code in there that could potentially go wrong. All right, so let's talk about proxy services, right? So there's a whole bunch of proxy services that you could potentially use. You could use something like PG Bouncer. There's another one called SQL Relay. The problem is that these need to run on compute, right? So there's no serverless version of these. So if we were to put this into a serverless application, then you'd have to write your own proxy or use one of these proxies, throw it on EC2, and of course, in a serverless application that is that's very much so shunned upon. I guess we don't want to do that. I guess the best you could do maybe is use something like Fargate would be a little bit better. But if you are going to go this route, then there is something called Amazon RDS proxy, which is potentially worth using. Now, Amazon RDS proxy just became GA a couple of weeks ago, I think. The question is it the silver bullet? Does it solve all your problems? I really like this service, and I like it because it does pool and share database connections. So you can have thousands and thousands of connections from Lambda functions. It will take all those connections, it will pool those and only use a few connections to your actual database itself, which is pretty cool. It will reroute requests on failover. This is something that if you ever did failover with DNS, or sorry, ever did failover with RDS before, you had to use something like DNS in order to do the failover. That can take a lot of time. This actually changes it within the proxy itself. You don't even lose the connections from your Lambda functions, and it gives you about a 66% reduction in that failover time. The other cool thing here is you can use those IAM credentials for your database access control. So those are all stored in Secrets Manager. And then you can do it's pretty easy. You just set up the Lambda function to have the right permission to connect to that. And then that will give the permissions to connect through all the way to the database on the end. So no more storing or having to recycle, I guess refresh your credentials and store those in the Lambda function or put them in parameter store or something like that and have to look them up. So this is actually pretty cool feature that you can do. There's also a really cool feature called Connection Pool Maximum Connections, which allows you to set how many total connections can be generated from that particular RDS proxy. So if you are using that database and you're sharing it with other applications, then you can say, I only want to use 50% of the maximum connections available in order to allocate to my connection pools. And that's pretty cool because that way, again, if you have a large database cluster, you're not going to want to maintain a separate database cluster for every serverless application if you're using RDS. So this is a good way to mitigate that. Couple problems though. This only works on Amazon RDS, all right? And you still need to do the capacity planning. So if you are using Aurora Serverless, you can't use RDS proxy. And we'll talk about why there's still some problems with Aurora Serverless when it comes to this. So this is just something to think about because you still need to do capacity planning. Yes, you can limit the number of connection pools so you can get a lot more connections. You don't have to worry about it so much. But if you are going to, let's say, have a spike in connections and you weren't using something like buffering, then this database isn't going to scale automatically for you. This is something where you do have to worry about that connection pooling. You do have to worry about the capacity planning. The other thing about this is, again, in order to have that redundancy, which Aurora Serverless gives you right out of the box and have it in multiple zones, you do have to set up multiple RDS instances in order to form a cluster so that you do have that redundancy there, which oftentimes means you're spending a lot of money to just have a backup server running. And then it's an added cost. So it's not a lot of money, but depending on the size of your cluster, you do pay based on the size of your cluster. So it's a really good solution. I think it works for a majority of the use cases. If you're using Amazon RDS, definitely look at it because it can solve your problems immediately. But there are a couple other things that you need to think about in terms of where this fits into the mix. So the other thing that we could possibly do is manage the connections ourselves. And if we were to do that, we'd have to make sure we count open connections, close connections if it exceeded some sort of threshold, close sleeping connections, and then retry connections with some sort of exponential backoff. And so most people would be crazy to try to build this. I built this before Amazon RDS proxy existed, and I did it because it was a need that I had. I kept on exceeding my database connections, and I needed something to do, something to mitigate that for me. So I'm showing this to you now because I think there are applications for this approach, not telling you to use this specifically. If RDS proxy works for you, use RDS proxy. But there are some reasons why you might need to do this yourself, especially if you were using Aurora Serverless, for example, or you were using something else. So if you're using MongoDB and you have connection pooling issues there, which you can't get with a Lambda function, for example, this might be a way that you could potentially approach this. So just to give you a quick idea of how this approach would work, is essentially what we do is for MySQL anyways, is we query the process list, we get the total number of active connections. I'm going to go through this quickly because again, it's just sort of giving you an idea. We check some sort of connection ratio. Now this is important too, because if you think about Aurora Serverless scales when it meets certain thresholds. So I think it's 70% of the connections need to be used and a certain percentage of the CPU. So if you set this too low, then you would actually never trigger a scaling event in Aurora Serverless. So just something to think about. So we calculate the timeout. So if we see any zombie connections that are just sitting there, then we can be proactive and try to kill those. If there are no zombies, but we've already exceeded that ratio, then we can just terminate that connection. And then otherwise, we just try to kill any of those zombies that are older. We also want to make sure we close any connections with high time values. So we just query that process list again, kill those zombie connections. And then one of the things that RDS proxy won't necessarily do for you. And that's not to say that this is always a problem, but it does happen where, especially if you just use like the standard MySQL node package, for example, if you try to connect to the database and that connection dies somewhere in there or doesn't connect, then that's it. There's no retry built in and there's some issues there. So this actually adds the ability to retry these connections with exponential backoff. And the idea there is to say that if you have hundreds and hundreds of Lambda functions running and all your connections are used, that they're going to detect that they're now over the threshold. They're going to clear up some of those zombie connections. And if we try this with some sort of exponential backup, then eventually, hopefully, we get a connection. So if there's that error trying to connect, and there's a whole list of these errors that might happen, then we retry with jitter. If you're not familiar with jitter, it's something that Amazon came up with. It's kind of an interesting way to do it, rather than us just saying retry in 100 milliseconds, then 200 milliseconds, then 400 milliseconds, and 1600 milliseconds. Rather than that being very very exponential in that way, the problem is if you have 1,000 connections that try to happen at once and they're all backing off at the same rate, then you're just going to keep overwhelming the system. So we add some sort of randomness in there, right? The idea of jitter, two different ways to do it, full jitter or decorrelated jitter. The idea is just different ways that you create some sort of randomness between how systems try to reconnect. And then the question is, of course, probably is, does something like this actually work? I did this with Aurora Serverless, 90 connections, gig of memory in the Lambda function, simulated 500 users per second for a minute, with their average response time being about 41 milliseconds with 0 errors. So again, hold your applause. It is great. It works well. But again, if you can use something like RDS proxy, if that makes sense in your system, then I would definitely do something like that. There are plenty of other reasons why you might need to manage this yourself, because RDS proxy, like I said, only works with RDS proxy, or only it works with RDS. And there are plenty of other connection-based systems out there that you might need to manage. So I think the real thing here is we shouldn't have to do this. And there are things that are getting better. So we mentioned Amazon Aurora Serverless. This is a really great tool. You get all kinds of great stuff out of the box. It scales automatically for you. It's got redundancy built in, great stuff. It doesn't solve that max connections issue, and you can't use RDS proxy with this. So if you are overwhelming that database with spikes and you try to create 2,000 connections to a database that only has 1,000 available connections, you're going to get that to cut off on you. And then it might scale, but you're going to have that issue where you're going to lose all that data if you don't have that buffered. If you buffer that data, you also run into the problem of potentially not triggering the database to scale, which is another issue. So there's a couple of things in there that you have to think about when using Aurora Serverless. I really like it, though. I'm a big fan of it. The other thing is the Aurora Serverless Data API. This is another thing that is really, really cool. I love this because it doesn't require a VPC. And anytime I don't need a VPC, especially for small workloads, is a win for me. But it does have slower throughput, right? The setup time for this is about 150 milliseconds, 100 milliseconds or so. Once you start using it, and you're using warm queries, it's not quite as bad, especially if you do HTTP keep alive, but it's still not quite ready for synchronous workloads. Great for asynchronous workloads. In a pinch, I've used it for synchronous workloads, especially if you're like, I don't want to set up a VPC just because I have to query one small bit of data. It works especially good if you can warm the data and save that in the Lambda function, for example. So you only have to worry about that slower connection time every once in a while. But it is great, especially on the back end of something like DynamoDB streams, for example. I love using it for that because then you don't have to worry about any VPCs and you can still connect to your relational database, and it's happening asynchronously. So if it takes a little bit longer, it's not that big of a deal. And then also we have Amazon RDS proxy. Like I mentioned, again, added cost still doesn't necessarily address all of the auto scaling things that you need to deal with. So just all of these things have their trade-offs. Figure out what one is best for your particular application if you need to use relational databases. All right, so let's talk about third-party APIs. This is another very, very common thing that we need to do. So just like with RDS or with relational databases, we want to make sure we implement a good caching strategy. We want to buffer events for throttling and durability, right? We don't want to overwhelm those downstream APIs. So if we can buffer them, we don't need immediate feedback. That works for us. And then the other thing we want to think about is implementing circuit breakers. So this is something that really should just be built into AWS and have some patterns for you. They don't quite exist yet, so hopefully this will be something that happens. But I do want to talk about the circuit breaker because this is something that a lot of people aren't necessarily familiar with, but can add a tremendous amount of durability and a tremendous amount of resiliency to your application, and can also make you a good netizen, if people are still using that word. I told you I have gray in my beard, so I don't know if that's still a thing. But you can be a good internet citizen and not overwhelm other APIs. Because the worst thing you want to do is when an API is having a problem and running slow, throw more work at it and see if that resolves the problem, which it's not going to. All right, so we look at this, and this will take a standard approach, API gateway to Lambda function. And let's say we want to call the Stripe API. Now, we know the Stripe API is notoriously unreliable. That's not actually true, but most of the time you're not going to be dealing with something as reliable as the Stripe API. Could even be something you wrote. So if we were just to send a message to that Stripe API synchronously, wait for the response to come back, and this is the happy path. Okay, everything worked great. As Julian mentioned right from the beginning, though, Werner Vogel's everything fails all the time. So if we get a failure here, we need to think about ways in which we can not continue to send data or continue to send requests to that Stripe API. We want to find some way to back off those requests. So what we want to do is put some sort of a status check in here. And I'm just representing this with the decision box, but essentially this would happen within the Lambda function. And then we want to use some sort of a cache that can store information about the number of retries we've had, whether or not the circuit is open or not. So I'm using DynamoDB here because I want to avoid using a VPC. And the reason why I want to avoid using a VPC is because to call out to the Stripe API, I would have to have a NAT gateway set up, and that's going to cost more money. If you're in a VPC already and you already have the NAT gateway and you're dealing with it, then I would use Elasticache because it's going to be super cheap, and it's going to be really, really fast, and the throughput is amazing. But basically what you want to do is you want to be able to check that DynamoDB or that Elasticache for the current status of the circuit. So if the circuit is what is called closed, right? If you think of a light switch, you close that light switch, the electricity can flow. If that circuit is closed, then we are going to go ahead and send the request to the Stripe API. Now, I want to be clear about this too, where the Lambda function is going to check for the status only if it doesn't already have that cache. And we'll talk about that in a minute, but we don't want to be calling DynamoDB every single request, especially if it's a high velocity call. We don't want that many requests to DynamoDB. So if the request is, or if the circuit is closed and the Stripe API responds back to us successfully, that goes to the Lambda function. We respond back to the API gateway, send it back to our client. And in this particular case, the client could be anything. The client actually could be an SQS queue. We might not need the API gateway in there. It could be another service. It could be directly from a web browser. Plenty of different clients that could possibly be. But let's say that Stripe API fails and that returns back to Lambda and says, I timed out, or there's some issue with this or whatever. What we want to do is update our DynamoDB or our Elasticache and let it know that we now have some sort of failure that is building up in there. And typically what we want to do is we actually want to wait. We want to wait until, or I should say, we can respond back to the customer, by the way, or to that client and say, hey, we've got a failure. We can't make that connection right now. What we want to do is make sure that there's some sort of a connection. We don't want to update that DynamoDB table every time it fails. We want to wait until some sort of threshold is made. So once that status is marked as, so once we reach that threshold, we then want to mark it as open, right? And that could be anything. We could wait till there were 1,000 failures. We could wait till there was 10 failures. But once we mark it as open, then we're not even going to try to connect to the Stripe API. Instead, we're just going to respond directly back to the client and say, no, that API is not working right now. Now, obviously, we can't just do that and then never connect to the Stripe API again. So every once in a while, we're going to do what's called a half open request. Now, if that fails, so again, we can send multiple ones. It doesn't have to be a ton. It could just be one. But if that fails, then we respond back to Lambda and say, hey, it failed. We don't have to do anything different because the circuit's already open. But if that eventually comes back and says, hey, I'm working again, then we want to go ahead and update our cache. And then we can go ahead and switch the circuit back into the closed mode. So a couple of things here is cache your cache with warm functions. And what I mean by that is your Lambda functions have a global scope, and you can keep track of how many failures there are in the global scope. You can keep track of whether or not the circuit is open or closed. And you should put some logic in there that says, if it now has exceeded 100, then I'm going to go ahead and make sure I tell the DynamoDB table that the circuit is open. Or if it's open and I'm getting a couple of requests, then maybe every 100 requests, I check the DynamoDB to see if the circuit's open. If it's not, then maybe I try a half open request. So unfortunately, this logic has to be built in yourself, but it is extremely effective way to do it. And it's just a nice way to coordinate Lambda functions across one another. You do want to use a reasonable failure count. Like I said, if you have 1,000 requests per second, then you might want to fail after 1,000 requests. If you have 1,000 requests per day, then maybe you want to fail after 5 bad requests, for example. So you want to just be conscious of that, about what the velocity is, and tie that to the failure count. The other thing is to understand item potency. So if you're not familiar with item potency, essentially what that means is that if a operation is item potent, then it can be sent multiple times and it has the same side effect. If you were charging a credit card and you sent in charge this credit card, charge this credit card, charge this credit card, and you sent the same event in 3 times, then it's possible that credit card could get charged 3 times and it wouldn't recognize them all as the same event. And so for most things, it's probably not that big of a deal if the same event goes in more than once. It would matter with a credit card. Luckily, the Stripe API has a very cool item potent ID that you can use, and you could just use some hash of the record or something like that you could use. Not everything has that, so just something to be aware of. All right, and if we start thinking about quotas, here's something that a lot of people are like, oh, I can just turn the concurrency down on my Lambda function. Well, if I have a quota of 250 requests per minute, if my concurrency is set to 250, that just means it can only do 250 at the same exact time. That doesn't mean it's going to limit it to 250 per minute. So setting the concurrency down really has no effect on the frequency of those calls. If you were to just use stateless functions, and you were to say, okay, we're just going to go ahead and keep calling the API, and maybe we'll keep track of how many we've done within a function itself, that's not going to be coordinated, and again, you could still potentially exceed that, or potentially not utilize the full amount. If you were to use step functions using the standard workflows, that'd be very expensive. You could potentially do this with the express workflows. That's a different pattern that you could potentially explore. If you were to add state, this is another thing. So if I was to add something that, maybe I add a DynamoDB table that keeps track of that data. If I was to add that state, that doesn't necessarily prevent needless invocations. So if I say, oh, 250 requests have been made already, and I have to check every single time to make sure that that's not exceeded, that could potentially be a problem. So all those invocations are going to still have to happen, and you're just going to end up paying more for the Lambda function to spin up and say, oh, I'm over quota, I can't make the actual call. So the question is, can we build a better system? If we did, I'd want it to be 100% serverless, cost-effective, scalable, resilient, efficient, and of course, coordinated. So I do have this pattern called the Lambda orchestrator. You can take a picture of the QR code and go to the blog post about it. But let's say we have a Gmail API that has 250 quota units per minute. What we would do is set up a single function that would be our Lambda orchestrator with a concurrency of 1. We would set up a SQS and a DynamoDB table, and then a CloudWatch rule that triggers our Lambda orchestrator every minute. Now, again, if our quotas are based on minutes, then again, there'd be a small delay here, but for the most part, this works really well. So we trigger that Lambda orchestrator that checks DynamoDB to see whether or not we are over quota for our current minute or current time frame, because this could be per minute, this could be per hour, per day, whatever that is. If we are not over quota, then it's going to query the SQS and pull down a batch of records. If for some reason there's a failure when it tries to load that or whatever, we have our DLQ in the background to make sure that those messages go there. We can also directly send any messages to that DLQ from our Lambda orchestrator if there's something wrong with that particular message. But then what we do is, again, we check the status. That would be through that DynamoDB table. And then we can use a fan out pattern and send these to the Lambda workers. The Lambda workers are all the exact same function. They're just concurrent executions of it. Those, if any one of those fails, because we're gonna send these messages out asynchronously. We're going to trigger these asynchronously. We can attach a DLQ, to the end of these, or we could even use destinations, and we could do something different with destinations. But essentially, we're going to capture any failed call this way, and then those will all call that Gmail API. It responds back. Everything looks good, and that data gets written to where it needs to get written to, or do whatever it needs to do. If it's just sending an email, then it just does that. If it actually has to contact something like DynamoDB, then it can do that as well. If it fails, then we can update DynamoDB and let it know that it's failed. So you can kind of build the circuit breaker pattern in here as well. We can also take those messages and write them back to the main SQS, so we can do some sort of retry. And then, of course, if the status is now marked as failed, then the Lambda orchestrator can go ahead and say, okay, we're not processing right now. So this is a great pattern in the sense that it can have both the throttling built in, it can have the circuit breaker built in, and it will have all that buffering and durability from an SQS queue to stage these things. So I use the Gmail API here because I built this for an instance where we use the Gmail API sending messages where there was a hard quota. And so if you had 1,000 messages in your SQS queue, we could, it would take us 4 minutes to send those. But that's fine because the way that the system worked is it would abide by those rules. And if for some reason we make a mistake and we exceed the quota, we can go ahead and use our Lambda worker to put it back into the main SQS queue and retry that pattern. Okay, same thing with the half opens and all that kind of stuff. All right, so I want to talk quickly about decoupling our services. This is another way in which we can add a tremendous amount of resiliency. So first I want to talk about SNS. This has been a traditional way in which we would distribute or fan out requests to multiple services. So an SNS would take an asynchronous request in the sense where you basically pass it off to SNS. SNS says, okay, I got your message, and then your client only knows that your message was received. What happened after that, you do not know from the client standpoint. And I've always looked at SNS before we came along with EventBridge as sort of a separate event service itself. So this was something where I would often set up a separate service that just had an SNS topic in there that I would use as my essentially as my event bus. So SNS is great. You can send messages to SQS, email, HTTP, Lambda functions, SMS messages, and you can now attach SQS DLQs to it. So if for some reason it tries to write it to or send an email or hit HTTP or whatever, it'll have different failure modes in which you can potentially write those messages back to an SQS queue for you. So a good amount of sort of durability, resilience there that if it doesn't get to its final destination, you do have a way to capture that event. So a couple key points here is SNS has a well-defined API. So if you are thinking about, if you think about microservice design, you want to make sure you have a well-defined API so you can standardize the way that you write your messages or events to something like SNS. It does decouple those downstream processes, especially if you put like an SQS event in front of it or an SQS queue in front of it. And I'll show you that in just a minute. And it allows you to have multiple subscribers with message filters, right? So each one of these services, you can put a different filter on it. So you can say if X equals 1, 2, 3, then write it to this SQS queue. But if it equals 3, 2, 1, write it to this SQS queue. And there's different things you can do with that, similar to the message rules or the rules that we'll see with EventBridge. So a fun fact here is anytime you write something to SNS and that is eventually going to make its way to SQS, it is essentially guaranteed. It retries for something like 21 days, over 100,000 times. So again, when Armageddon comes or whatever, you'll actually still be writing SNS messages to SQS. You don't have to worry about those. One less thing to worry about when the end of the world comes. All right, so multicasting with EventBridge, this is something that is now sort of more recommended. There's a reason why EventBridge and SNS are two separate things. And there are use cases for SNS that don't fit into Amazon EventBridge, but Amazon EventBridge for, I guess, event-driven, event bus type stuff is a much better choice at this point. Still missing a few features that we hopefully will get soon. So same idea here with SNS. This is a asynchronous put events request to a bus. This time you get an event ID back, which is kind of cool because you can track that through or trace that through if you do want to see if a particular service is done. Like let's say that you write something to Amazon EventBridge, you send that event ID back to the consumer, and the consumer then can poll or something like that to check to see whether or not that event is done. That event ID could eventually write back to a DynamoDB table or some other lookup. So Amazon EventBridge, very similar to SNS. You can write to SQS, you can write to Lambda functions, but you can also do step functions. You can write to other event buses, plus there's like 16 other different services you can write to. These all have rules, so you can be very prescriptive about the rules. One thing that's great about the rules for EventBridge as opposed to the filters for SNS is EventBridge will read the data directly from the body or the event itself. Whereas with SNS, you actually have to send in message attributes separate to the content that you're sending in the message. So you have to do extra work on the front end to make sure that there's data for you to filter on the back end when you're using SNS. Whereas with EventBridge, you don't have to worry about that. So it's a much better process for that. So some key points. So you can have multiple subscribers. So again, you can have based off of some tiny bit of information. And of course, you can use patterns. You can use filters. There's all kinds of things that you can do based on something within the data itself or within the event itself. You can say, call this Lambda, call that Lambda, start this step function, and so forth. You can say, call this Lambda, write it to an SQS queue, start this step function, write it to another event bus, all with the same event. You have a lot of flexibility there. You can forward events to other accounts. So I've seen this pattern pop up quite a bit where people are building microservices in separate accounts under AWS. So they're using an event bridge within each account and then coordinating those event bridges to write to one another. And then right now there's 24 hours of automated retries built in, which is a really good feature just to say, look, if I try to write to that Lambda function and it doesn't, then I'm going to keep trying and keep trying and keep trying or get into SQS queue. So we'll try for 24 hours. There's no DLQs or anything like that yet, but again, that's something that I'm sure the team is going to be working on. So what's cool about these patterns and being able to use an event-driven approach is we can not only distribute these events to multiple services, but we can also implement all of those patterns we talked about. You can implement those for each individual service. So you take EventBridge, for example, you write something to EventBridge, you can immediately respond to the client saying, hey, we got your order. So I submit an order and it responds back and says, okay, wait, we got it. Now what we do is we have an order service. So we write a rule, EventBridge gets that message, it sends it through, goes into the SQS queue, and we want to limit it because we're writing, we're going to throttle it because we're writing to RDS. Then we can do that within our order service. But maybe we also have an alerting service, and we want to make sure we send an alert to let them know, send them a text message that they got it. We add another rule. We say, okay, order came in, write it to that SQS queue. We have some quotas to deal with. We can use our quota pattern. We can use some other pattern to limit the amount of stuff that's happening there. And then we have a billing service. So another, that event comes in, we route it to that SQS queue that calls the Stripe API. Maybe there's some other concurrency thing happening there. And we can add really interesting things to these filters, and we can say that we only want to send a text message when the order is complete, when that detail type matches order complete. Or we only want to charge your credit card if the numeric value of the total is greater than 0. So maybe we have a free ebook that we give away and we don't want to bill the card if that's the case. And so a couple key points here is that those filters can be used to selectively trigger different services, not just triggering a Lambda function here or there, but like actually trigger different services themselves. Each one of these services operates independently. And if we can't write to that SQS queue for the Twilio, for the alerting service, EventBridge is going to keep retrying that. And eventually the SQS queue is going to get that. And once the SQS queue gets that, if that keeps on failing because the Twilio API is down or we've exceeded our quota, eventually because of all this other resiliency we've built in and all these patterns we use, that message is eventually going to get sent. And then that's the idea where we can essentially manage that throttling and quotas per service. And if we are doing anything asynchronously here, seriously look into Lambda destinations because it is a much better way to capture, especially failed events, because it allows you to see like the stack trace and stuff. So just quickly, some other non-serverless components. We mentioned those managed services. So think about something like Elasticsearch or Elasticache. I mean, at some point you're going to run into limits there. So depending on how your application is built, you might want to think about dealing with those. We've got other cloud services. So think about MongoDB Atlas, or again Elasticsearch, or some of these other services that are using APIs that you need to mitigate. You need to mitigate traffic to. You've got legacy systems. You start looking at enterprise systems, and there is a lot of COBOL out there and a lot of old systems that do not scale very well. So these are other things that you might need to start thinking about integrating with, and even our own serverless APIs. So if we think about limiting the amount of traffic that can go through, we want to maybe protect against denial of wallet or something like that. We might say this API we expect a certain amount of traffic on, so we want to limit the concurrent connections. We maybe want to add some throttling. We want to add some quotas to the API. Those are other things that could potentially affect it. So even if you're calling another serverless API that you've built, there's potentially limits there that you need to think about. And then the important thing to remember here is that these are inevitable, right? So you need to know the limits of all of your components. And again, most of this is published. If you're doing some components yourself and you're like calling your own serverless APIs, understand what that might be. Again, use that good caching strategy. Caching is always a good method for having some resiliency and mitigating some of that downstream pressure. But again, just remember, make sure that you size your downstream system so that it should be able to handle whatever the throughput of your system is if that cache goes down. Asynchronous processes with distributed systems, the likelihood of you connecting 5 or 6 synchronous calls all together and everything working perfectly is a fantasy to think that would happen perfectly every single time. You're going to have failure in there. Asynchronous processes separates that out. It breaks up those workloads. It gives you all kinds of tools and ability to retry these different things. Buffering and throttling events to distributed systems, again, another really, really good practice. No reason to try to call something immediately if you don't need to. If you can design your application to have some sort of a throttling built in and you can buffer those events, great to handle spikes in workloads without having to worry about capacity planning. So always something that is good to have in the mix. And then we didn't really talk about this one, but super important is eventual consistency. So this is just a concept in distributed systems where if you're not writing everything in real time, meaning you're buffering things, maybe things are going into the SQS queue, it's very possible that you could send a update to a database that gets buffered in an SQS queue and eventually gets processed, and then you have another service that calls it and tries to look it up. You might write data, call it, and it's not updated yet. That is perfectly fine. That happens all the time. You see it happen all the time in distributed systems. If you think there's a way to fix that and that you can have everything perfect in real time, go research the CAP theorem and you'll realize why that is not possible. But just something to embrace it and utilize it. And then finally, that's it. So check out my blog and my podcasts, newsletter. my DynamoDB toolbox, one of my open source projects, Lambda API, and GitHub, and my Twitter account.
Awesome, Jeremy. That was great. Yeah, I think it's quite a relevant topic because you're very rarely going to build. Yeah, you're very rarely going to build systems that scale infinitely. Or if you figure it out, you can tell us how to do it.
I will.
Yeah, we've got a quick question on YouTube. Yeah, so what tools? Wait, that was the wrong question. YouTube, come back to me. Oh, no, there we go. Yeah, so what happens to open connections when you change the creds? Are they still alive? So when you rotate the credentials, I think it was around the proxy, the RDS proxy, data proxy.
Yeah, so I'm not 100% sure, but the way that it works is that once the connection's established from your Lambda function to RDS proxy, that connection is maintained separately and is authenticated separately based on IAM credentials. And then it is the proxy itself that manages the connection to the database. So if your credentials are rotated, I think it would work fine. Because I don't think you'd lose the connections to you wouldn't lose the connections from Lambda to RDS proxy, and then it automatically handles failover already. So I think that would work. I think that would work just fine.
Yeah, that would be my guess as well. But yeah, I'm not 100% sure.
I'm not 100% sure, but I think that would. Yeah.
Yeah. So another question from Javier Mendoza Gomez. What tools would you use to trace failures in an event bridge approach? CloudWatch logs with correlation IDs can be difficult. What would you recommend?
Yeah, unfortunately, there are no tracing headers being passed through to events with CloudWatch. I'm sorry, with EventBridge. I actually just had a really good talk with Ader Lessa about this, because if you look at the serverless lens, they do not recommend EventBridge as a messaging bus in the serverless lens right now, because it doesn't have tracing and because it doesn't have DLQs and some of these other things. Now, I look at it and I say, what I essentially do with EventBridge is I just add a rule that captures every event and writes all those events. And then if there's any failures, I try to manage that myself. It would be much better if those DLQs existed and things like that, and if tracing was there. What I typically do is if I have a trace header or I have a correlation ID, I just set up my scripts that post to EventBridge. I set those up to include that trace ID in the message itself, and then it's just up to the system to do it. So it is not the best way to do it. It's certainly not as smooth as tracing SQS and some of these other things right now. But for the time being, that's how I do it. I don't know if that's the best way to do it, but that's what I do.
Yeah, I think just following up on that, there's another question about, what's the failure state of EventBridge if it doesn't deliver the events in 24 hours? You've kind of partially answered it there. Obviously, there's no DLQ. Yeah, so what is that failure state, for someone who's never touched it before?
Yeah, so at 24 hours, if the message is not delivered in 24 hours, it is gone. It goes into the ether. Yeah. So I mean, the thing to remember with EventBridge though, and something like the durability of it, or the uptime of it, is to say, if you're delivering to, because I didn't mention this in my talk, but let's say you're sending a message to or an event to a Lambda function. So the way that works is that it'll actually invoke the Lambda function asynchronously. So you don't actually need the Lambda function itself to run. What you need is the Lambda service to accept the event. So those two different things. So what happens is EventBridge just needs to be able to connect to the Lambda service, which is completely independent of your Lambda function altogether. And so to assume that the Lambda service would not be available for 24 hours is kind of insane to think that would be the case. So as soon as the Lambda service accepts the event, then that buffers it for your function. And if your function then is throttled, for example, you get 6 hours of retries built into the asynchronous processing queue. If it eventually times out, it will write it to a DLQ. You can set up destinations, things like that. So there are all of that failover and processing, or like the DLQs and stuff, will happen at the Lambda level, as long as Event Bridge can deliver it to the Lambda function. And it's the same thing with like SQS. Like, is SQS going to be down for 24 hours? No. So as soon as it gets to SQS, even if whatever is attached to SQS isn't working or is broken, it'll just stay buffered in SQS. And that happens for pretty much all the services. I mean, similar to things like the step function, all you need to do is a state machine to kick off. If your functions or anything else is failing under the state machine, that's independent of Event Bridge, and Event Bridge is now out of the picture.
Yeah, I think it's reasonable to expect AWS not to have a 24-hour failure. I think the longest failure they've ever had has been 6 hours in one region, and that was a good few years ago. So yeah, I think that is, I think it's a reasonable approach to assume there's not going to be a complete failure. There are potential issues around durability of Event Bridge if there is a failure in region. So I think, are there any other questions? No more questions. Yeah, so thanks, Jeremy. Awesome talk, really detailed. You've listened to your podcast, read your email, your weekly email a lot. You've also got these new short little intro videos coming out. Anything else you want to tell the people to sign up to? And
no, I mean, check out, I did, I released the new serverless reference architectures project. That's something that I released about a month ago. There's a lot more work that's happening there, but a lot of the patterns that I talk about, there's just so many patterns, and some of them are slightly different. So I think for a lot of people, they look at a particular pattern like, oh, that doesn't work because of whatever. There's probably a slight variation of it that might work. And so what we're trying to do with this project is get people to contribute to it and create these diagrams that let people see how they work and have those variations there as well. So hopefully people get comfortable, because one of the things that I try to push, and I know, Ant, you try to push it as well, is think serverless first. I mean, honestly, if there's something you think you can't do, you probably just need to rethink it. And if you rethink it, then you're probably going to come up with a way that you can do it with serverless. And the last bit of advice I'll offer just around that is, even if you say, well, it's not going to be super efficient to do it with serverless. Here's the question. Let's say that it adds a second of latency to your, to your application or something to do one particular part serverless. Is it easier to do that and have the 1 second delay and have that done in like 2 days? Or does it make more sense to try to get that down to 100 milliseconds, for example, and spend 5 weeks trying to build out your container cluster and all this other stuff, right? So if you can take the approach where you can get 90% of the way there with serverless with a couple of workarounds, I say do that. And then you can always re-engineer, because again, it takes so little time to do these things with serverless. Just do it that way first. And then if you want to optimize the application later and say, no, we really need containers to do this particular part of the workload, then great, do that. Don't do that first.
Yeah, no, I'm a massive fan of that approach. I understand what your problem is by actually implementing something up front rather than spending a lot of time doing it in theory. And then when it comes to reality, find a whole lot of edges, build it as quickly as possible in serverless. If there are edges that don't work for serverless, then you can refactor later. But yeah, serverless first. Is definitely a viable strategy. Yeah, thank you very much.
Awesome.
Is it lunchtime in Boston?
Past lunchtime, but that's all right.
Okay, cool. Well, enjoy the rest of your day.
All right.
Cool.
Thanks,
Jeremy. Next up, we've got Ben Piggin from Theodo. And where is Ben? Ben has joined us. There we go. And Ben's going to be talking about performance optimization of serverless platforms. A pretty important topic because there are obviously performance concerns and monetary concerns, and there are obviously constraints within your serverless environment. So optimizing your serverless environment for performance helps to alleviate a lot of those constraints. So I'm going to hand over to Ben.
Awesome. Thank you so much. Let me just share my screen. Nice. All right. So hi, everyone. I hope you're well, wherever you are. I'm really happy to be here. Very gratifying to be placed amongst such auspicious speakers as well. So yeah, a bunch of really cool talks from Julian and Jeremy. So thank you both for that. I'm going to be talking about improving the performance of your serverless application. So it's largely going to be about how we implemented Kaizen or continuous improvement on our project at Theodo. and also a little bit of learnings along the way about what impacted or how we fixed some performance problems in one of our serverless projects. Cool. So I'm Ben Piggin. I'm a developer at Theodore UK. We're a startup that helps other startups launch digital products and also help global companies work at startup speed. So the project I'm going to be talking about is a company called HomeServe Now, which are a startup within a larger FTSE 100 now company called HomeServe, which you might have heard of. So the sort of disruptive insurance tech company, and largely the work that we were doing for them revolved around their traders app. So this is a React Native phone application that sort of leads engineers along the journey when they're attending a repair. So they can pick up jobs for various customers with it, then select those jobs, and it sort of leads them through the flow. So it might be a gas engineer fixing your boiler, and they can fill in all of their details and parts and then receive payment all through the app without need for ideally calling anyone or any other involvement. So this involves like big cost reductions. So yeah, that's a really cool project that we're involved with. The tech stack was DynamoDB, Lambda, Node.js on the back end, and a React web app and React Native app, as you just said, on the front end, and TypeScript throughout. So initially when we started on the project, it was clear that there are quite a few performance issues. So some of the main user tasks on the admin web app, like loading all the jobs, would take around like 14 seconds for a sort of hard refresh of the homepage, and then saving a job in the app take about like 1.5 seconds. Of loading all your jobs would take 2 to 3 seconds, which would happen quite often, like on user journeys through the app. So it's maybe a little bit of a painful user experience. And after a few months and all of our performance improvements, we managed to get this down to about 1.2 seconds for the admin panel and loading jobs, and saving a job and loading jobs are now done in half a second. So how did we get there? So I want to talk a little bit about Kaizen. And some of you may know what this is, but this is Japanese for good change or continuous improvement. So the basis of this, I'm not going to go fully into the 6 steps and everything, but you pick something that you want to improve. So this could be anything. For us, it was performance of Lambdas and Lambda response time. But it could be, I don't know, sales for your company, like how you market, like any metric that you can track and you want to improve. So the next step is to understand what the current situation is and what are your problems. You then come up with ideas on how to improve it, implement those ideas and see what's changed and check for improvement. It's also about fostering a culture of improvement itself, so that everyone in the team is aligned like on this one goal. So companies, this has come from companies like Toyota in Japan, this is really like intrinsic in their company culture. So everyone at every level is encouraged to sort of make changes for the better, like at whatever level they're working at in the company. And this is like comes naturally to them, and they automatically assume responsibility over this. So yeah, one example of this, I've always like encountered Kaizen for the first time in software development. So it's always been like really attached to software development for me. But I do quite a lot of climbing, and Japanese climbers are like really incredible. There's like a lot of really good Japanese climbers in the world at the moment, like the best climbers in the world. And when asked, like I was watching an interview with a Japanese American climber, and when asked like, what do you think is the difference? Like, why are there so many good Japanese climbers? He said the culture of Kaizen in Japan. Like Americans, when they go to climbing gyms, they do it for exercise and like to get fit. But Japanese people go to climbing gyms to get better at climbing. It's just that focus on the one goal. So how do we achieve this in the project, and how is it relevant? So the format that Kaizen took for us was basically 3 30-minute sessions every week that just happened after lunch. And these were quite like free form sessions, and they involved the whole team. So free form just meant that anybody could contribute and come up with things. So have you read anything about power tuning Lambdas, how memory is going to affect like computation speed and the speed of performance of the Lambda, like an article on cold starts and how package size affects it. So it meant that like we really were exposed to a lot of like articles and ideas, because everybody had the freedom to just say what they liked. And it's also like involving the whole team was also really important, sort of unifying the whole team around this one problem. And it meant that everybody sort of was encouraged to take responsibility over this problem and suggest improvements. And it's also like a safe space to experiment and learn together. A lot of us, for some of us, me included, like we're new to serverless. So you can just look up, find best practices and sort of learn together, which is quite an effective way of distributing knowledge quickly across the team. So yeah, we sort of gravitated towards Thunder as our main observability. Obviously, there are good alternatives, and Julian's talked about a lot about how X-Ray looks really cool. But for us, Thunder became our main sort of point of call. So most of our Kaizen sessions would sort of start with somebody sharing their screen, looking at Thunder, what is the current state of our Lambda performance. So Thunder, the website at least, had some really cool features that made this really easy. So we could see, like, at a glance, what the average duration over various timescales, so like the last month, the last week, the last day of various endpoints. And there's also, if you clicked into each individual Lambda, there are really cool just waterfall charts of like where our time was going. So for this one, it's 2 calls to DynamoDB, it's call to API gateway, 2 SQS, and 2 more writes to Dynamo. So stuff like this made it really easy to see like where our time was going and where the biggest performance hit we were taking was. And the whole being able to see what your average speed was over a particular time made it really easy to see the impact of our actions, you know, like merge this change yesterday, like what is the average speed for today been like have we hit our target? Have we had an impact? The other thing I want to talk about, this is the only GIF I could find for accountability, so thanks to whoever made this. Yes, this is something that we also found really important in terms of motivating, like, why are we actually doing this? So at Theodo, we tend to have weekly reviews to stakeholders where we demo the product and we talk about what we did last week and justify our cost to the client. So one of the things we started with is like arguing that performance is really important in applications, like saying people leave websites if things don't load within 2 seconds, and how it really impacts the UX in the app. Like, you're not going to have people loving your app if stuff is, they have to wait consistently throughout the journey for quite a long time. So having argued to stakeholders that this is really important, we should do something, we then had to justify week on week, like what we were doing to fix it. Also, the weekly demos of the app, quite often when you start a job, you'd see the performance, like whoever was demoing would be like, and now we have to wait for the job to start. So when you've got like incentives like that driving you, it can focus your mind as a team on really bringing the improvements that are going to affect this metric the most and deliver improvements. So yeah, that's very important in your own problem solving, to how can you generate that sort of accountability for yourself? Like, who are you going to show this to? What targets are you going to make visible to other people and say, like, this is where we want to get it? So for us, we had this big graph and a standard of like less than 1 second response time that we wanted to get everything down to. So it was really important for us to, one, make sure that we could see improvements on this graph just for average Lambda response time, and that we could give stakeholders statistics like the average duration of this function has gone down by 36%. We're on our target of under a second. The cost for this function is down by 100%. Like, it doesn't cost you anything, and it was costing you like whatever per month. So stuff like that is quite important. Cool. So I hope that was interesting about sort of general problem solving strategy and how it helped us. I'm now going to talk, I guess, a bit more specifically about our technical strategy and how we delivered quite large improvements to Lambda performance. So I'm going to talk a little bit about refactoring and how we removed side effects, improved DB schema, and then more of it is going to be a focus on cold start times and how to improve those. So step one for us was refactor the code so we can see what it's doing. And we found for Node.js that MIDI.js is like a really nice design pattern for handlers. So we had a lot of handlers that pretty much started with the same sort of boilerplate. Like, you've got an event and you need to pass your body and you need to check whether your path parameters are there, essentially check whether you've got a bad request or not. Or a malformed request rather. So every handler would start like, okay, check if this is undefined, check if this is undefined, get my path parameters and pass my data. And those, because we were using TypeScript, we would then have to cast in order to get type safety, but obviously we're not sure whether the data is going to be malformed or not. And obviously for error handling, the entire thing would be wrapped in a try catch as well. So MIDI is a really nice pattern where you can encapsulate a lot of that logic in middlewares that you can then use. So for parsing the body, you just use this parse JSON middleware that will just handle it for you. And then on the first line, you've just got direct access to event.body because it's already been parsed. And you can do this really nice thing where you generate JSON schemas from your TypeScript types. So all you have to write is the type for your body, generate a JSON schema from that, and then error handling, basically generating 400s with specific error cases for whichever bit of your request is malformed. It's done automatically and it will automatically generate an error response. And similarly for error handling, like it's all just done as part of the middleware, so you don't have to worry. You can just throw exceptions within the body of your handler and they will be caught and processed. And the same thing with generating a response object. You can just return whatever object you want to return as part of this handler, and then the response handler will just put that in a correct response object with the status code and everything for you. So we found this is a really nice pattern just to separate business logic from sort of Lambda boilerplate entirely, so we could just focus on, okay, what is it actually doing and where are the slow bits? So when we did this, we sort of realized that a large contribution to slowness is side effects. So things like third-party SMSs or push notifications. And even though these were side effects, because of the way that we called them essentially as just post requests, they would take a long time and we would wait for the response. So this would add like seconds when you're just trying to like save something or do something else within the app. You'd be waiting behind like this SMS or push notification being sent. So step one was sort of move that to just invoke another Lambda synchronously that will get kicked off and handle it. Long term, we want to move to event bridge and just event driven architecture, so we can just subscribe to particular Lambdas being triggered, and we can just not worry about SMSs being sent at all. It can just return whatever it needs to and carry on regardless. In addition to this, like using promise.all, just making sure that if you really do have to kick off requests and they're independent, you can just do it simultaneously, which sped up a lot of stuff as well. Sort of low-hanging fruit. I'm not going to go that deep into DynamoDB, but it was also a lot of what we did. So basically, read the DynamoDB book by Alex Debris. It's really good. And yeah, major takeaways is that single table design patterns are kind of hard. You need to think about what your access patterns are going to be for a long time in advance before you sort of bake them into your schema. And yeah, just make sure you're using things like overloaded indexes with hashtags and sort keys and all of that good stuff. So a lot of, again, the improvements is just making sure our queries were efficient, getting rid of full scans, making sure we were using indexes where necessary. Cool. So cold starts, I'm going to go a bit more into depth because I think it was kind of a cool like Kaizen problem solving journey that we went through. So by the time we got to this, like the running our code section was pretty good. So we got most of our Lambdas down to like under a second, like some of them were just like half a second. But our statistics were still like not great. And obviously looking in Thunder, we were like, okay, why are all of these cold starts taking like 2 or 3 seconds when the code is executing in like 0.5? So cold starts are basically, I'm sure you'll know what cold starts are, but in case anyone doesn't, if there's not already an instance in the cloud that's ready to run your code, then AWS is going to have to start one for you. So it will download your code, start a container, bootstrap, whatever runtime it needs, in our case, Node.js, and then it will run your code. So for us, that process was taking a long time, like 1.5 seconds plus. So, oh yeah, the other thing about cold starts is like, it's not necessarily infrequently used Lambdas. Like if an instance is already running and it's running your Lambda and you get another request, you'll have to kick up another instance as well. So it's something, so we did some reading around this and saw that it's something you could mitigate by keeping Lambdas warm and using provision concurrency. And we wanted to see basically whether we could avoid this just for cost purposes, basically, like we didn't really want to pay for that. If we could avoid it, then we would do. So looking at our Lambdas and trying to guess why they were taking such a long time to cold start, it was maybe a little bit obvious. So all of our Lambdas were like nearing the package size limit for AWS. They were like 50 meg each. So we're sort of like, okay, this looks like it might be the explanation. So it's led to the hypothesis of like, okay, decreasing package size will probably make cold starts faster. Might as well give it a try. And given that cold starts in Node.js relatively fast, like it looked like you could get down to sort of 200 millisecond response times. Like we'll see how near we can get to that as like a standard. Yeah, one of the interesting thing, I do recommend like reading up on how cold starts work with different runtimes in different languages, because it's really interesting. Like, yeah, whether Java is like a compiled language is maybe a bit slower because you need the compilation step, whereas like scripting languages like JavaScript or Python tend to be faster because it's like just-in-time compilation and all of that good stuff. It's really interesting. Not that relevant to what we were doing, but good bedtime reading if you're so inclined. Cool. So step one was like install serverless Webpack, which you'll be familiar with if you're a front-end developer. So yeah, and start packaging our Lambdas individually instead of as one huge object. So the way that the service that we were trying to make faster was set up, we had all of our handlers as like instance methods on a really large service object. So it basically means that everything was packaged with all the dependencies in one go, and even individually packaging our Lambdas and adding Webpack, everything would just get in that one package. So output of this was good try, but not yet. So our next step was to install a really cool plugin called Webpack Bundle Analyzer, which basically gives you an output of why is your package so big and what are the biggest contributions in this really cool like interactive chart, which I can't interact with because it's a photo, but would recommend downloading it. It's really cool. So from this, we could see that like the biggest contribution is actually the AWS SDK to our packages. And obviously we've got a bunch of other dependencies as well. But for the most part, they were large because the AWS SDK was in there. So the next step was pretty obvious, just exclude the AWS SDK. So you can just force exclude this as part of your Webpack options in serverless.yaml, and make sure you add it as a external in your Webpack config. Otherwise, you'll lose your Thunder traces, which happened to us and was very confusing for a while. So don't forget to do that. Cool. And the other thing, so after doing this, we realized that, okay, that's great. It's gone down by a lot. But there was still a lot of packages hanging around that just looked like it shouldn't be there. Like Moment and Lodash were mysteriously there, even though they weren't used in the actual handler code. So we then did some digging and found that those handlers, like we had a bunch of just utilities.ts files around that had a lot of exported methods that were used sometimes by multiple Lambdas, sometimes by just one. And basically what happened if you imported like a function, even if it didn't have any dependencies itself, you'd get for free all of the dependencies at the top of the utilities.ts file. So a lot of this was like splitting handlers out from this sort of big object, putting them in their own folder, isolating all the utility functions that they needed, and just putting them next to that handler, basically improving the code structure. But also as a side effect, like not packaging dependencies that you just don't need. Cool. So the impact of this is our overweight cat 50 meg packages went down to speedy grommet 250 kilobyte ones. And our cold start time went from about 1.5 seconds to 0.4, which was pretty great for us because for our use case, like less than half a second delay for the user really wasn't that bad. And the Lambda execution time was already under half a second anyway. So we sort of hit our target of under a second, and like it felt fast when you're in the app on the app end. So we were pretty pleased that we didn't have to use something like provision concurrency, and that cold start times in Node.js are fast enough that you can sort of rely on this. So yeah. Cool. So yeah, takeaways. I hope you learned stuff about Kaizen and problem solving that you potentially apply to either Lambda performance or just general problems on your own projects. And also, yeah, if your tech stack is Node.js, hope you maybe learned something about Lambda performance and cold starts and Webpack. And yeah, thanks for listening. Theodo UK, we're a really cool place to work. I really love working here. There's a bit of a recruitment drive because we're currently recruiting. So yeah, we really like serverless. We got like big serverless architectures in production right now. So yeah, if you're interested and it seems like a cool place to you, then feel free to like DM me on Twitter. My Twitter handle is at the bottom if you want to chat. But yeah, thank you for listening.
Thanks, Ben. So the most important question we've got is, what is it like working with Ben Ellaby?
Well, see, he's now competing. Now I know people like Julian and Jeremy with their enormous knowledge of AWS exists. Then maybe Ben is worried he seemed less impressive. But it's great working with Ben. He's a super knowledgeable guy. Yeah.
So we've got 2 questions quickly on YouTube. So you inherited an existing code base with issues. Was the observability tooling already in place, or was the tooling added to help rectify the issues when the project started?
The second, we added Thundra when we started the project. Yeah, just someone who's now left the project, but I think somebody that enjoyed using it on a previous one. But yeah, found it like really good for like diagnosing performance problems, like using the waterfall stuff, but also just generally for sort of alerts when certain lambdas were like erroring out. Was really cool. Like it puts the information, like primary, like sort of thing I like most about it. It just put the information like quite clearly. Like you just go to tabs and see like what's erroring, like what's the slowest stuff, and it's just really easy to just seek out where sort of errors are happening that might go unnoticed otherwise. Yeah.
So how quickly were you able to put Thundra in? You know, you inherited this project, and I was like, okay, you don't have the observability. You really need to understand what's happening there. Was it like weeks, months, days? What kind of timelines was like the time to value on once you said, okay, we're going to do it and getting stats?
In general, so Thundra happened pretty quickly. It was in the first days of the project. I think like working out the true implications of then what to do was like months. Yeah, like we started the project in February. And we're just about to roll off actually. So yeah, it's been like 6 months, and a lot of the changes that we've made are like only now coming to fruition. I think like major learning is like doing stuff incrementally is like actually a really good way of doing things. Like we were like as a project focused mostly on feature delivery, like on writing new features for the app, like coming up with new functionality, like generating value for HomeServe now is still trying to like grow their user base and like prove their sort of cost saving viability. So although all of this, I don't know, performance tech improvement stuff was like really important, it's also like, yeah, just what can we do sort of every week to like make stuff better. So I think, yeah, from that perspective, it's like important to identify your problems really well and figure out like what's the smallest thing we can do like week on week to improve it.
Yeah, that's awesome. So Thundra basically gave you that visibility to drive this performance improvement, so you could measure it essentially. That's cool. So another question here. So was there a massive difference between using Webpack and the built version of TypeScript of TS?
I don't quite understand the question. Sorry. So using Webpack and not using Webpack, or?
Yeah, I think so. Yeah, because using TypeScript. Yeah, you know, what was the size difference between the two? Because you talked about the time difference. You know,
sure.
from like 2 seconds to 0.4, what it was.
I think. Yeah, largely, probably the biggest difference that we got was excluding the AWS SDK. Obviously, it's a little bit of a risky thing to do because you're no longer tied to a specific version that you can control. It's sort of whatever version AWS is running on their container. But for us, it's like we thought it was a low risk that they'd introduce some sort of breaking change that would impact us, and they haven't yet. So yeah, that was the biggest. That took our package size down from like 50 meg to probably about 10 meg per Lambda, I think. And then from then it was just, a goal of like splitting up the code, like isolating stuff, like all the good front end stuff that you probably do all the time if you're worried about package size, like loading specific modules and that sort of stuff. So I think, Webpack was just useful as sort of an iterative thing. Like you could build it, use that analyzer, figure out, and then, that was the value of it to us.
It is interesting. I always use Rollup for all of my functions, which are similar to Webpack. It does a lot of tree shaking. Have you, out of interest, have you started to look at the new version 3 of the AWS SDK? I don't know if you realize they're completely re-engineering the entire AWS SDK for JavaScript into more modular packages. And you can actually, there's open GitHub repo, they're doing it in the open. Which will enable you to just bring in the dependencies you need. So if you're working with DynamoDB, it just brings in those Dynamo dependencies or S3 instead of bringing everything in and these shared components. Have you guys looked at that at all?
We haven't. It does sound awesome though. Yeah, like I think I'm now in this world where like front end has become back end, and we're all talking about like code splitting and that sort of stuff, which is cool to see. But yeah, no, it sounds good. Like if we had the choice, like we definitely import like only the stuff we needed for a specific Lambda. I think if it was really only going to increase package size, like I think we noticed that like it still can. Your cold start time does start to increase quite a lot, like as your package size grows, like early on. Like we found it's sort of like it grows almost exponentially, like going from 250 kilobytes to like 1 or 2 meg, like can be the difference between like 0.4 and over a second of like cold start time, at least from what we found. But obviously a lot of this is sort of it's difficult to perform the experiments because it's gonna, I have no idea how like AWS loads your code. So in terms of like how many packages is it loading and how is it loading them, it's probably going to vary based on that. So it's quite difficult to know in advance like what the impact of like say like bringing a particular dependency in is going to be.
There's a lot of science, well, not science. You can go really deep on trying to optimize Node.js and how it loads the code, because the node resolution algorithm does a lot of work. If you're shipping a bundled code, the node resolution algorithm just doesn't run at all because everything's in one file. When you're shipping unbundled code, particularly with lots of dependencies, you've got that algorithm running on every single dependency. And just that, never mind, even if they're the same size, it'll be slower loading lots of modules versus loading one module. It's a massive rabbit hole trying to performance optimize Node.js. Let's quickly see if there's any other questions. We've got one more from Leo here. Okay, just saying you can achieve some of the things, setting AWS SDK as dev dependency, compiling TypeScript with TSC and serverless will package it all easily. Okay, that's more of a comment rather than a question. So I think that's it. Thank you very much. Ben Ellaby, anything to say?
No, thanks so much, Ben. Other than to mention, Ant, I believe you've got a course coming up.
Yeah. Oh, yeah. Thanks for reminding. Yeah. So we've got on homeschool.dev, which is Senzo's online learning platform. We've got 2 courses live at the moment. One is an advanced React course. So if you're a front-end developer, it's great. It goes through how to ship production React applications. So how to use things like Learner.js, Storybook.js to build a component system, continuous integration, continuous development. So if you really want to take it from that next level and how to actually do React in production, that's a great course to do. Then, of course, we've got the Burning Monk himself, Jan Shuri. We've got his production-ready serverless course running from the 1st of September, and that's live now. We do have discount code. It's SLS August, all in capitals. You can go check the meetup.com serverless-London page, and the code's there, but it's SLS August, all in capitals, and I'll give you 10% off either of those courses. The big difference with the homeschool courses is that they are mentored courses. You work within a cohort. We have a Discord channel where the instructors are available at any time. So if you get stuck there, if you get stuck at any point, you can ask questions. So for example, you get direct access to Jan. Ask a question, and he's on that every day. He always responds, and then there's weekly Q&As at the end of it. So the main thing about the homeschool course is that they're mentored. You work in a cohort. You've got people to work with you. You're not just left to yourself. And having direct access to Jan is huge. So it gives you a massive jump up in your serverless learning if you want to do our courses. So yeah, go to homeschool.dev, check out those courses, use the code SLS August, all caps, and you'll get 10% off. I think that's it. Thanks, Ben. And Ben.
Awesome. Thanks, everyone.
Cool. We'll chat to you all later.